Well, hey guys, today we're going to talk about complex numbers. Now, remember yesterday when we were solving like x squared is equal to something like 25, and we asked ourselves, what number times itself is 25? Or we'd do the square root on both sides because what undoes squared? Square root. And we'd be left with x is equal to 5. Nah, Smith, since we use the square root to solve, x is equal to plus or minus 5. That was a lot of fun, wasn't it? Sure it was. But today what we're going to do is something like this. X squared plus 1 is equal to 0. What would be the first thing you would do here? You would subtract 1. X squared is equal to negative 1. Then, if we thought about this on a conceptual level, what number times itself is negative 1? That's kind of weird, right? Because think about it. A positive times a positive is positive. And we have a negative number times a negative number. What does that give us? Positive. So anything times itself is always going to be positive, with the exception of, let's write 0. So anything times itself will never be negative. So back in the day, we used to write no real solution, right? But we're big boys and girls now. So instead of that, what we're going to do is we are going to go and use a square root to unsquare this. So the square root of x squared is just x equals plus or minus the square root of negative 1. But nothing times itself is negative 1. So that brings us to a weird new thing. We're going to a new charted territories. You guys are going to learn new numbers today. The square root of negative 1 is also known as a number called I. Smith, did you just say a number I? I sure did. I is an imaginary number. All right, so the square root of negative 1 is also known as I, which brings us to a new family of numbers, complex numbers. Complex numbers are anything that's in the form A plus BI. A plus BI. I don't know why I didn't center this. Sorry, y'all. But anyways, A is going to be the real component of this number. The real numbers. We've always only been working with A. But B is the imaginary component. And that's the new stuff that we're going to talk about today. All right, so let's start off with some simplifying. Simplifying is just like we did yesterday, except that it's going to be a little bit different. Let's talk about the square root of negative 4, the square root of negative 12, and 4 times the square root of negative 27. All right, here's 3 examples. The first one, just like yesterday, we talked about square root of 4. Square root of 4 is 2, but because it's got this negative, yesterday we talked about if we have the square root of A times B is the same thing as the square root of A times the square root of B. Think about this one like this. This is the square root of negative 1 times 4. You with me on that? So that means this would be square root of negative 1 times the square root of 4. Square root of negative 1 is, we just talked about that up here, that is I. Square root of 4 is 2. I'm going to put the 2 in front. Just, you know how we always have 2x? X2 looks weird, right? So would I2. So instead I got 2I. I just switched the order here. But it's the same way as before. It's just, square root of 4 is 2, but because it's negative, we're going to slap an I on there as well. Let's talk about root 12. What I would do, rather than, Smith, do I have to do all this work each time? No. This is just me showing you the concept. Let's talk about root 12. 12 breaks down to, now yesterday we talked about 3 and 4. Let's do 6 and 2 today. Does it matter? No, still comes out. A 2 comes out, and a 3 got left behind, right? So you got 2 root 3. The only thing is because this is negative, we have to have the imaginary component to it. We have to have I. So this is going to be 2I root 3. Here's the thing, y'all. As soon as you see a radical, or excuse me, a negative inside the radical, you're going to have an I. All right, let's talk about 4 root negative 27. Make a tree with negative root 27. 9 and 3. 3 and 3. What can come out? Well, we already got 4 out. A 3 can come out. And a 3 gets left behind. But remember, there is a negative, so we have to have an I there. So this is going to be 12I root 3. Smith, do I have to have the I between the two things? What if I did it as 12 root 3I? Each teacher gets a little bit, has different feelings about this. That is technically correct. However, here's where it gets messy. If you have 12 root 3I, right, now it looks like the I is inside the radical, which if I is inside the radical, that is the square root of negative 1, which, as we all know, is the 4th root of negative 1, which takes us to a whole nother world. So here's the thing. It's not that it's wrong. We just like to have the I between the regular number and the radical so that there's no mistaking that it's inside. Word? Word. All right. Let's do some fun stuff with complex. First of all, let's talk about add and subtract complex numbers. I'm just going to do one of these because I'm pretty sure you're going to catch on to this. Parentheses 6 plus 4I minus the quantity of 13 minus 12I. I don't know about you, but me, subtraction creeps me out. If I have a group minus a group, I'm going to change this minus to plus. That's how I roll. But if I change this to plus, I got to change the signs inside of here, right? So this would be negative, positive, the opposite of each one. Right? So now it's 6 plus 4I plus negative 13 plus 12I. All right? Here's the thing, y'all. We have a real component and an imaginary. You're just going to combine like terms, just like we've always done. 6 plus 4I, they're not like terms. I can't add them, but 6 and negative 13 is negative 7. And then 4I plus 12I is plus 16I. Right? When you're adding and subtracting, combine like terms. That's it. Keep that simple. Multiplying is where it gets a little tricky. Multiplying is a little fancy. Let's talk about some quick things here. What's root 5 times root 5? Many of you probably thought root 25, which is 5. And here's the thing. This is not wrong. This root 25 is not wrong. But for what we're about to get into, I don't want you to think of it like that. What I want you to think of, radical 5 times itself is just straight up 5. What I'd rather you think of it as the square root of 5 squared, which square root and squared undo each other, and you're left with 5, right? Right, so let's do another one. What is root 17 times root 17? 17, right? What about root stick dude times root stick dude? That'd just be straight up stick dude, right? Root stick dude times root stick dude is stick dude. Here's the problem. Well, no, let's talk about this. What about root negative 1 times root negative 1? Now, some of you might think, wait a second, negative 1 times negative 1 is positive 1, so it'd be root 1, which is 1. But no, you can't think of it like that. Instead, the way you have to think of it is root negative 1 squared, then the radical undoes squared. Root negative 1 times root negative 1 is negative 1. Right? You can even see it with stick dude. Root stick dude times root stick dude is stick dude. Well, what if stick dude is negative? What if stick dude is negative 5? Root negative 5 times root negative 5 is still going to be negative 5. Negative and negative is still going to come out when you're using radicals. Which brings us to an interesting fact. If root negative 1 times root negative 1 is equal to negative 1, that means that I, which is root negative 1, I squared is also negative 1. That's an important thing I need you to know, y'all. I squared is negative 1. You heard? Let's do a couple examples here. Let's talk about some multiplying here. Suppose we did 5i times negative 2 plus I. 5i times negative 2 plus I. Well, this is just a distributing problem, right? We have 5i times, we got a set of parentheses. You're going to distribute like this. So 5i times negative 2, negative 10i. 5i times I is plus 5i squared. The thing is, what did we just get done talking about? I squared is negative 1. So in other words, what we have here is negative 10. This is just a regular I. That's root negative 1. But plus 5 times I squared, we just said is negative 1. So 5 times negative 1 is negative 5. To put this in complex a plus bi form, we're going to put this as negative 5 minus 10i. Because this is a regular, our real component, we're going to put that first, and then negative 10 comes after. So it would be negative 5 minus 10i. Let's do another one. How about 7 minus 4i times negative 1 plus 2i. Now, before we get started, what does this look like? This looks like foiling, or the double distributive property. What we're going to do is we're going to take this first 7, excuse me, I want to do that in another color, distribute the 7, but then we're also going to distribute the 4 to both of these. Foiling, right? So go ahead and foil real quick. I'll race you. Ready, go. I got this. Did you get that? Hopefully you got something like this. So now we're going to combine like terms. This is going to be negative 7 because that's the only constant. 14i plus 4i is plus 18i minus, well, here's the thing though. Instead of minus 8i squared, what is I squared? Well, here, we'll do this. Minus 8i squared. What is I squared though? It is indeed negative 1. What's negative 8 times negative 1? This would be plus 8. All right, I squared made this negative 8 become plus 8. So now combine like terms again, because now we have new constants. Negative 7 plus 8 is 1 plus 18i. That would be your final answer. All right, I got one more section, and then I'll let you be. This next section is called the conjugate. Now, the conjugate is kind of a weird thing. Let me give an example here. Let's say I give you 4 plus 5i. I'm going to show you what the conjugate is, and I'm going to show you a couple examples, and let's see if you can understand what a conjugate is. The conjugate to 4 plus 5i is going to be 4 minus 5i. All right? We're not going to go and multiply it or anything else yet, but right now let's give you another conjugate. How about 3 minus 8i? The conjugate here would be 3 plus 8i. All right, I'm going to give you one more. Let's see if you understand what a conjugate is. Negative 7 plus 12i. Make a guess. Here's what it is. You ready? It's -7 minus 12i. Conjugate only affects the plus or minus. Has nothing to do with the first term's positivity or negativity. It's just, or its sign, I should say. It's just plus becomes minus, minus becomes plus. Both terms remain the same otherwise. Now, that's going to help us divide. I kind of lied. I guess there's this other section too, but there's only one example. Divide complex numbers. Let's give an example of 5 plus 3i over 1 minus 2i. Yesterday we talked about how it's impolite, it's rude manners to leave radicals in the denominator. Well, it turns out it's also rude to have an imaginary number in the denominator. It's not cool. So we have to get this 2i out of the denominator. The way we're going to do that is we're going to multiply both the top and the bottom by the conjugate. Now, when we multiply by the conjugate of the denominator, some magical things happen when we multiply the top and bottom by the conjugate of the denominator. Now, the conjugate would be 1 plus 2i. Some magical things are going to happen here. What I want you to do is or multiply the top out and multiply the bottom. I'll do it as well. Go ahead and press pause, or go ahead and do it, and we'll see if we agree. All right, so foiling it out or multiplying it out, I got this, which looks like even more of a mess than what we started with, right? But here's the thing. On the top, combined like terms, we're going to have 5 plus 13i minus 6, right? Because this is plus 6. I squared would be -1, so it become minus 6 over, the bottom is going to be 1. 2i minus 2i cancels. We're going to be plus 4. The -4, I squared is -1, so it becomes plus 4. But look at that. The denominator, the i's are gone. The conjugate eliminates the i's. So the top is going to become -1 plus 13i over 5. Now, there's no I in the denominator, so that is an acceptable answer. So when you're dividing by a complex number, if you have an imaginary in the denominator, you're going to multiply by the conjugate. We'll practice some more in class. Smith out!